sorry, my slides didn't have time to get translated, but most of my slides are pictures, so it should be quite easy, I hope, to follow. Right, I want to talk about part of diastole, which has not been concentrated on enough, I think. As we know, diastole is a complicated process. There's decline of the myocardial active state, and there's problems. There's connective tissue is very important, which gives rise to what I'm going to talk about, suction. There's rapid changes in pressures. There's the transmitral flow. There's interaction of the right ventricle and pericardium, and atrial systole. So several mechanisms are involved. So here's another way of looking at it. You can see as the pressure declines, we have the relaxation and to the end of systole, the pressure, and there are a number of different processes. There's a relaxation of the muscle. There's diastolic suction, which I'll talk about. There's ventricular interaction, and many things are involved. The elastic properties of the heart, the extent of relaxation in the myocyte, pericardium is affected, and also the coronary. So I'm going to talk about twisting of the heart, because this is very important to the function of the myocardium and in diastolic filling. Actually, it was first described by an Englishman in 1628, well, first described in the West, sorry, and he noticed that the heart rotates and twists. And this is an example. If you go to a cardiac surgery, you will see the heart rotates like this, okay? We're not aware of it, because most of the time we do echo or we do MRI, and the heart looks like this. You just see this, okay? We don't see the twisting motion, which is very important. So the heart is constructed with the fibers wrapped around to make this twisting motion. And it's important because the myocyte contracts by 20%, but the volume changes by 60%. So the transfer of the myocyte contraction into a volume change, you need this kind of structure of the heart. So can we measure the twisting? Well, we couldn't for a long time, but now we've got some method, ventricular rotation measurement, using speckle tracking. I think many of you know all about this now. It's a very useful technique. And this excellent paper by Notomi in Circulation used this technique to look at rotation, and you can in twisting and untwisting. But remember, this technique is looking at rotation, okay, here and here, like that, okay? But the heart actually is moving obliquely. It's moving like that, okay? And none of our techniques, no strain rate, nothing, actually measures the oblique motion. So what we're measuring is still artificial. So this paper shows very nicely how the heart twists and contracts, then at the end, the aortic valve closure, the pressure drops and untwisting takes place. And you'll see here, this is the peak untwisting. At this point is the peak intraventricular pressure gradient, okay? It's a pressure gradient between the left atrium and the ventricle, and the pressure gradient within the ventricle, which causes the blood to come in, okay? So this is closely related to the untwisting of the heart. The heart screws like that, then untwists to get the increased gradient, pressure gradient. On exercise, this is very important. Okay, you can see there's more twisting, massive untwisting, considerable untwisting, mitral valve opening, the pressure gradient is negative, the blood rushes in, the heart is now relaxing, the twisting is relaxing, you have the peak E here, the peak flow, and then mid-diastasis, mid-diastole. And the twisting velocity and diastolic function correlate. All these things are highly significant. early diastolic peak velocity, the time to the early diastolic peak velocity, and the acceleration. So this process is very closely linked. The untwisting rate relates to the twist rate. This is important because it means how hard your heart twists determines how fast it will untwist. Okay? So systole is controlling early diastole. Okay? It's a very important concept that the systole is actually determining early diastole. The untwisting rate also relates very strongly to the interventricular pressure gradient, which is causing the suction, the blood to come in to the heart. On exercise, it's even more important, because on exercise, the heart rate goes up, diastole gets shorter, so you have to get the blood in faster. Okay? So on exercise, you've got very little time. The heart squeezes up and it has to suck the blood in very fast. Okay? So like athletes have very powerful hearts, and when their heart relaxes, they spring back and suck the blood in. Okay? So this is a very important process. This is just another way of expressing how this process all links up, and the whole heart works together. The timing is very important. The timing is very important, that all these things happen together. Now we know, if you like, pressures rather than, we know that there's a negative pressure gradient here, and this was shown many years ago to be due to suction. In fact, it was first described, apart from Harvey, in 1956 in this lovely experiment where they took the heart, they put a tube in here through the mitral valve, blocked the mitral valve, and there's a reservoir here, saline reservoir. Okay, pressure is less, but what happens when the heart contracted, as it relaxed, it sucked the blood in. Okay, so proving that diastolic suction exists. I'll cut this out, it's too many words. So, in the normal heart, here's the apical velocity, apical pressure, which is a measure of suction, and you can see in heart failure, there's no suction. Okay? So, the systole is not good, therefore the diastolic thinning is not good. You can't get the blood out, you can't get the blood in. So the cardiac output goes down. How can we measure? Can we measure that diastolic suction? Well, there are one way. There's some slides missing here. Sorry, I'll skip that. So, how can we measure it? Well, one thing is to look at this ring. Now, the muscles are connected to the mitral valve ring. And when the heart contracts, the ring moves down, which not only the ventricle gets smaller, but as the ring moves down, it pulls blood into the atrium. Okay? It actually creates suction in the atrium, so the blood comes into the atrium. When the ring springs back, the blood is coming in, the ring is going round the blood that comes in, so it helps the filling. Okay? So this movement up and down is very important. Okay? Down, it sucks the blood into the atrium. Up, it helps the filling. So if you lose the movement, you lose a large part of your function. And we know that the long axis, the long ventricular axis, the movement of the ring is very important. And the stroke volume in the left heart is 60% is due to this motion. So how can we measure ventricular suction? Well, one way is to measure this motion. Okay, it relates to the ventricular suction. That's the E prime. And we know the E prime is a matter of, it actually measures other things. Active relaxation, the restoring forces, which is the diastolic suction. Okay, which again, as I said, it's like a spring. You push the spring, how hard you push, how fast it comes back. Okay. And this lengthening load is actually the atrial pressure, which is more important with atrial systole than early diastole. And systole and diastole are linked. if you look at SM and EM, or S prime and E prime, they're very closely linked. And we did this study a long time ago in Hong Kong. We also showed that if you use this technique, the EM, the early diastolic velocity, is very low, as you expected in patients with HFnEF or HFpEF, diastolic heart failure, but so is the systolic function reduced as well. Okay? So it's not just diastolic failure. Its systolic function is not good as well. And there are abnormalities of systolic function. And this technique actually is very predictive of mortality in big communicative heart study, Copenhagen City Heart Study. So the other way we can measure it is the mitral flow propagation, which I think many of you know about. It's not an easy technique, but if you measure the slope of this relationship, you can get some measure of how fast the blood is going into the ventricle. And in our studies of HFpEF patients, we found that the VP at rest was the same as the control patients, but on exercise was very low. So the change in the VP was half what it was in the controls. So the suction was reduced. This shows again, here's at rest, no difference, but on exercise it rises much less than the control. So the propagation is less, the suction is less. And it relates to the exercise capacity. Here's mitral propagation and lateral, the SM relates, and it also, there was a reduction of the long axis function. So I won't preempt the next talk, but just I want to emphasize that the importance of the left ventricular rotation or twisting reduces ventricular suction, which reduces early diastolic filling. This is with the correct slide. This is another way of doing it. You can measure the suction by this technique I told you about. Also, you can use this new technique of measuring the gradient across the mitral valve inflow. So recoil, that recoil of the heart is very important, and there are a number of things that affect it. One is the collagen, the extracellular matrix, the collagen around the heart. And we know the collagen is different types, type 1 and type 3. And it changes. With type 1 it is more common in heart failure. The heart is more stiffer. And the other one is titin, which is in the myocyte, which provides stiffness to the myocyte. So here's the collagen on the outside of the myocyte, and inside is the titin springs, which tend to control the myocyte relaxation. So both of these things are controlling the stiffness of the heart. And if you look at the myocardial collagen in patients with hypertension or with or without heart failure, you can see that total collagen is up a little bit, but up a lot in patients with HFpEF. So the collagen is increased, making the heart more difficult to relax, but also more difficult to contract. This is titin. Shows you here the titin molecule. It's a big molecule, has an effect of when the heart contracts, the titin is stretched. When the heart relaxes, the titin will come back. So it will help to relax the heart. But it also changes in certain situations. There's different isoforms of titin, which can increase the stiffness of the heart. I think the time's running out. So aging is very important. As we age, our hearts get stiffer, and we know that affects the collagen, not only in our faces, but also in the heart. So that leads to loss of ventricular suction, especially on exercise. And what we need is an anti-aging. This is some work we did a long time ago showing a very strong correlation of age or long axis functions on the E wave particularly. Here you can see as you get older, that movement of the AV plane gets less. So just to conclude, I'm sorry I should have this in Chinese, but anyway, untwisting with recoil causes suction, which is responsible for pulling the blood into the ventricle during early diastole. The heart is a suction pump. Okay. The extent and speed of the recoil and hence suction depend on the force of the previous systole and the amount of stored energy, rate of the myocyte relaxation, the state of tightenings within the myocyte, and the quality of the extracellular matrix. Reduced suction and hence reduced early diastolic filling is found in nearly all forms of heart failure and also is associated with normal aging. Exercise may slow the rate of reduction. Improving this fundamental property of the heart as a suction pump will require sophisticated therapy. I think it's not likely that any one drug will solve this problem. It's quite complicated to restore the whole function of the heart, the twisting, the untwisting, the movement of the AV plane, change of collagen, change of tightenings is a very complicated business. So I don't think that one little drug is going to do all that stuff. But it's going to be a difficult job to put right. And finally, systole and diastole are intimately connected, and there's essence only one cardiac cycle, and isolated diastolic dysfunction is extremely rare. Okay, thank you very much.